So this last set of possible homework problems might throw you for a little bit because they go back to talking about a technique that we used back in session 1 video where we looked at special triangles like 45-45-90 triangles and, more importantly, the 30-60-90 triangle. So let's take a look at this. The sine of t is equal to 3/5, okay, and is in the first quadrant. Find the cosine of t. Well, what we're going to do is we're going to draw a picture of this. This is the best way to solve the problem. So we're going to draw a 4-quadrant little plane here, and we'll notice that sine of t is equal to 3/5 and is in the first quadrant. So there's some point t in this first quadrant, and it has a relationship of 3/5 to theta, which I'm going to denote with a lowercase t right here. So according to SOHCAHTOA, the sine is the relationship of the opposite over hypotenuse. So from theta, we're going to go to the opposite side, which in this case is 3, which is my y distance here. And my x is unknown, we don't know that. And my hypotenuse is 5. So this is not on the unit circle, so we can't actually run to the unit circle for some help because we won't find it there, because this radius in this case is 5, it's not actually 1. So what this means is that we got to find this missing side x. Well, the Pythagorean theorem is going to help us here, because we can have x squared plus y squared equals hypotenuse squared, which is just a squared plus b squared equals c squared. So I'm going to plug in my x, which I don't know the value of x. I'm going to plug in my y, which is the value of 3, and I'm going to plug in my value of h, which is 5. So I'm going to have x squared plus 9 plus 20 is equal to 25. Subtract 9 from both sides using inverse operations. X squared is equal to 16. Then I'm going to take the square root of both sides here, and if I do so, what I have is x is equal to plus or minus the square root of 16, which is 4. Now, since I'm in the first quadrant, my x values in the first quadrant are positive, so my x is equal to 4. So x is equal to 4. I can make that look a little nicer just by erasing that and that. So now I can find my cosine of t, because the relationship of cosine is going to be adjacent over hypotenuse. And that's from theta right here, this angle, and the adjacent side would then be 4, and the hypotenuse side would then be 5. So the answer to cosine of t is the relationship of 4/5. Problem number 9 is going to go very similarly, except it's going to be a lot more challenging because instead of being in the first quadrant, we're in the third quadrant. So there's some point t in the third quadrant that has the relationship to theta of -1/3. So what I'm going to do is remember my cosine, listed up here, it's adjacent over hypotenuse. So my adjacent is going to be 1, and my hypotenuse is going to be 3. You'll notice that this is a -1/3, and since I'm in the third quadrant, my x value is going to be negative. So is my y value, but we're going to need to find that so I can get my sine of t. So what I'm going to do here is I'm going to use my Pythagorean theorem. So x squared plus y squared is equal to hypotenuse squared. So I'm going to plug in my -1 and square it, excuse me, and then I'm going to plug in my 3, which will get squared. So 1 plus, because -1 times -1 is 1, 1 plus y squared is equal to 9. Subtract 1 from both sides thanks to inverse operations. Y squared is equal to 8. Now, when I have my y squared equal to 8, I'm going to take the square root of both sides. If I do so, I'm going to have y is equal to plus or minus the square root of 8. Now, since I'm in the third quadrant, my y values are negative, and so that's going to make me choose this one. Please note that our hypotenuses will always be positive in each of these examples here. It keeps the system rolling, and we're just going to treat the hypotenuse as a positive distance, like a radius, excuse me, because the radius here is 3. Okay, so the square root of 8, we can do a little work on the square root of 8, because that is the product of square root of 4 and square root of 2, so 2 square roots of 2. So y is equal to -2 square roots of 2, and don't forget your negative. Negative 2 square roots of 2 is equal to y. And we don't want to forget our negative because when we go for the sine of t, which is going to be our opposite over hypotenuse, the answer to the problem, and I'll just kind of bring it out here since it's a little lost in the work here, that is going to be negative 2 square roots of 2 divided by our hypotenuse 3. And that way we have a negative y value, a negative x value, and that matches for the third quadrant. We can always check our answer by plugging this back into the unit circle here to see if we get our answer of 3. For these next two problems, we're going to use our knowledge of 30, 60, 90 triangles to solve the answer, because it says find the coordinates of a point on a circle with radius 10 corresponding to an angle of 60 degrees. Well, drawing a picture to save the day, I'm going to create a triangle in the first quadrant, and it has an angle of 60 degrees, and I'm not going to draw it to scale. All I need to do is mark my 60-degree angle here, which is going to be my theta, and the radius is 10. So this creates some point t up here and some theta down here. Now the big question is well, geez, how am I going to find anything just knowing what I know? Well, what's good about the 60-degree relationship here is we know our sine and cosine value. Now, this sine and cosine value would be if the radius was, instead of 10, if it was just 1. Then this would be 1/2, and this would be square root of 3 over 2. Now this is the relationship of sine and cosine, and this is going to be our cosine here, and this is going to be our sine here, on a unit circle with radius 1. But you can see that our radius is actually not 1 at all. Our radius here is 10. So what I see is that the relationship of the x value is 1/2 of 10. So we can put a 5 here. And that 5 is the key to unlocking the whole problem. Since we know that the cosine relationship, when you have a radius of 1, is half, or in this case, adjacent over hypotenuse, or 1 unit to 2 units, then essentially this can be rewritten as this adjacent side would be 5, and this hypotenuse side would be 10. Now to find my missing side y, we're just going to use the Pythagorean theorem. So we're going to have x squared, which plus y squared is equal to h squared, and our x in this case we know it's 5 squared. We don't know our y in this case, and we do know our h in this case, which is 10. So 25 plus y squared is equal to 100. Subtract 25 from both sides, inverse operation to solve for y squared, and that gives me 75. If I take the square root of both sides, then I'm going to have y is equal to plus or minus the square root of 75. Now we're going to be in the first quadrant, so we'll choose the plus here. So the square root of 75 can be broken to the square root of 25 and the square root of 3. So that means our y is going to be equal to positive 5 square roots of 3. So that is my y value, 5 square roots of 3. So I can erase this and this, because now I actually have my x and my y value. My distances along the bottom here, so this is going to be 5, and this is going to be 5 root 3. And that gives me that coordinate point t on the end of that triangle here. So in review, the thing that unlocked this whole thing was knowing that in the 60-degree triangle, my cosine was 1/2, which means that the relationship of cosine is adjacent to hypotenuse. Now, since the relationship is 1/2 the size, I just have to take my hypotenuse, divide it by 2, and I get my answer. So things just get a little bit trickier when we have an angle that's not in the first quadrant. We have to be a little bit more mindful of where things are, and 210 degrees is in the third quadrant. It's actually 30 degrees beyond the 180 degree angle, and that means I can make a reference angle, a nice right triangle. Should put my right angle in there. And this problem has a radius of 20. So we know from looking at this spot that this is negative square root of 3 over 2, and this is negative 1/2. Now this is not my answer to the problem here, and it's not my answer because this radius is not 1. This radius is 20. But I do see that my y value is that relationship of negative 1/2, or from theta here, of my 30 degree angle. This is going to be the opposite over hypotenuse. So this opposite side is negative 1/2. So it's a 1 opposite side to the 2 of the hypotenuse. Well, that means that this y distance is half the size of this hypotenuse. And since it's in the third quadrant, it's going to be negative. So there is the key that unlocks everything. So now we're going to use our x squared plus y squared equals h squared. And we're going to unlock the missing x-axis here. So I don't know my x-axis. I do know my y-axis. So here we go. And I do know my hypotenuse. So I have x squared plus 100 is equal to 400. Use a little inverse operations to solve for x squared, and x squared is equal to 300. So then I take the square root of both sides, so I'll show this over here. Square root of x squared is equal to square root of 300. You can see I sometimes like to put the radicals underneath so people can see the progression, like that. And sometimes I put them in the problem if you can see that this was just copied over here. So x is equal to plus or minus the square root of 300. Now since I'm in the third quadrant, my x's are negative, so I'm going to have a negative answer here. So the square root of 300 is the breakdown of the square root of 100 times the square root of 3. So x is equal to negative 10 square roots of 3. Now the reason why I'm simplifying these radicals is that's really good math grammar, but another reason to simplify these radicals is to show you the 30, 60, 90 pattern. The pattern of the 30, 60, 90 is that it's usually 1 square root of 3, and then 2. This is the relationship or the ratios of 30, 60, 90 triangles, that there's going to be the short side is always half the length of the hypotenuse, and then the longer side is always going to be the shorter length times square root of 3. So 5 square root of 3, 10, negative 10 square root of 3, 20. Again, short side is half the hypotenuse. Multiply the short side by square root of 3 to get the distance of the exact distance of the long side, and then you have your hypotenuse. So it's a pretty cool relationship. And again, this homework section being so far away from session 1, you might have forgotten, like, oh, we literally talked about 30, 60, 90 triangles. But we also talked about 45, 90 triangles as well. So for this problem, we have a radius of 15 and an angle corresponding to 135 degrees. Now 135 degrees is in the second quadrant. And in the second quadrant, if we create a reference angle from that 135 degrees, you'll see that this is going to be a 45, 90 triangle. So this radius is 15, this is my 45 degree angle here, and this is my right triangle. Now what we have to do is we have to find our y value, and we have to find our x value in the second coordinate. Now, honestly, we could go into the complicated square root of 2 over 2-ness of this point, but what's kind of nice about 45, 90 triangles is you do have x squared plus y squared is equal to 15. But if you remember back to session 1, I just want x squared plus x squared equals 15, because in a 45, 90 triangle, both legs are the same size. So as long as I figure out x, I can actually plug that in for y. So 2x squared is equal to 15, because this is 1x squared and 1x squared to make 2x squared. Divide both sides by 2. X squared is equal to, now I know what you might want to do is you might want to go 7.5, but I know where I need to go, so I'm going to keep this as a radical here. Now I'm noticing that I forgot my little squares. which I will add now and compute. Sorry about that, I should have computed that earlier when I did so over here. So 15 squared is going to be 225 divided by 2. Now I'm going to take the square root of both sides, and what's kind of cool is that I can kind of show you what happens in either case. So if I take this one and take the square root of both sides, which is the square root of x squared, and this would then be the square root of 225 over 2, then I get x is equal to plus or minus the square root of 225 over 2, which I would break that into 225 divided by the square root of 2. So I'm going to break this into two separate division of radicals, which I can do because of the properties of radicals. So now x is equal to plus or minus the square root of 225 is just 15 over square root of 2. Now you can see that I've also could have like went from this step here to this step here, knowing that the square root of a square is itself, as long as you adjust for the plus minus, and then we also have the square root of 2. So this is going to be important. I'm not actually going to define the plus or minus because I'm looking at two sides of my triangle here. So I'm going to multiply top and bottom by square root of 2, and the reason why I'm doing this is I'm trying to get rid of the square root in the denominator. So my numerator is now 15 square roots of 2, and my denominator is now just 2. So x is equal to plus or minus square root of 15 over square root of 15, or 15 square root of 2 over 2. So this is 15 square root of 2 over 2, and since we're in the second quadrant, I'm going to take the minus from my plus minus and put it here. And this is going to be 15 square roots of 2 over 2, or the positive value for this value, y, which happens to be equal to my x, but positive. So now, if I'm looking for the coordinates of this point right here, then I just have to be a little careful and put the negative in the correct place. This is negative 15 square roots of 2 over 2, and this is going to be positive 15 square roots of 2 over 2 for my x, which happens to be this distance from here to here, and my y, which happens to be this distance from here to here. Kind of wild getting out those old things that we learned a couple weeks ago, but man, those special triangles sure are handy. And thank you for watching.